Hi everyone, welcome back. Hope you had a good time in the breakout rooms and either ma- ma- hello, made some more progress on linear regression or segued into starting with logistic regression. And now that you've looked, many of you at least have refamiliarized yourself with the concept of logistic regression and looked perhaps at least some running of it in state. I thought we'd just debrief on the early parts of the exercise just to remind us and get some grounding in how to interpret these results and what we can do with them and how we can use data to do computations for us. And I am indeed recording this. Thank you, anybody who was going to remind me. Well, as soon as I put it out there that somebody should remind me, then I somehow stuck it in my head as well. So it's been recorded. I can't post these till tonight or tomorrow morning. It turns out, and I learned the hard way yesterday, that processing the videos, so I record them in a framework called what's called Camtasia, and then I have to export them as MP4 files. And when I export with Zoom running, because the computer, it crashes my computer. And I finally learned, realized, and I experienced several times that was the problem. As soon as I turn off Zoom, I can process the videos easily, and then I can upload them to YouTube. So anyway, let's talk logistic and the sort of refamiliarize ourselves with, we talked about the basics, but let's put it into action here with our first data set where we're looking at, we now have taken for the CE charges data. And let me, sorry, I need to share my screen. I am going to share my screen. We've taken the CE charges data, and we've used that to estimate the 90th percentile of charges, and we've created a binary representation of having high costs by flagging each record in the data set as whether or not their charges were greater than the 90th percentile of charges. So we've taken something that was initially on a continuum, and for reasons discussed in the exercise, are reanalyzing this binarized at some upper threshold. And one of the first things I had you look at just to get your feet wet again with logistic regression was the relationship between having high medical expenditures and sex of the person, biological sex. Let's just pause for a moment. Certainly last week, if you were in the class, I could have asked you pretty much the same question, but we wouldn't have used logistic regression to answer it. So I want to show the connection between sort of the old way of doing things and this new way, but talk about why this new way, which is not new for anyone, but this new way this week is more generalizable and expandable compared to what we did last week. So if I ask you to look at, compare the proportion of males and females who had high medical expenditures by our cutoff, I've gone ahead and I've created this binary measure that's a 1 if the expenditures for any individual are greater than the 90th percentile, 0 if not, and I have 87 out of 800, about 10%. Does that make sense that we'd have 10% ones and 90% zeros roughly? That makes sense, right? Because we put the cut at the 90th percentile, so only 10% of the samples should be greater than the 90th percentile. So we also have sex. And so if you were in class last week and I said let's compare the proportions of, let's just, nothing fancy, don't worry about confidence intervals or measures of association yet, just give me the proportion of males and the proportion of females who have high medical expenditures. What might be the easiest way to do that without thinking about regression? I've got an outcome that's binary and a correlate or potential predictor that's binary. How can I just look at that in a data analysis workshop 1 approach? Yes, we could tabulate, exactly. And so maybe I would tabulate, let's do it this way. We'll do tabulate high medical expenditures by sex. Let's see what this looks like. And so our column variable here is sex, 1 for males, 0 for females. The variable name is labeled, but I didn't take the time here to label the specific values. But if I wanted to represent the proportion of males and the proportion of females who had high expenditures and not do the math by hand, not take 52 out of 492, for example, to figure out the percentage of females, what could I could just add to this command what option to get that percentage. Anybody remember? Well, I'll give it to you. Column? Okay. So we've got, what, 10.5%, 10.57% of the males had high medical expenditures versus 9.33% of the females. So we can see that the percentage who have males who have medical expenditures is greater than females. If we want to see whether this is statistically significant, we could add the CHI2 here. It's not statistically significant, and it's not a large difference percentage-wise, but it's nevertheless something we can look at in this table. I'm asking you to do the same analysis via logistic regression, which quite honestly is a bit more tedious, but it's sort of building the foundation for something that we can build on more easily than these cross tabulations and single comparisons. So how do we go about doing this? Well, the first command I introduced you for doing logistic regression, instead of using the command regress like we do in Stata, we use the command logit, for example. And I give it my binary outcome, and then I give it my predictor, in this case male, which is binary as well, encoded as a 1 for males and a 0 for females, right? So I'm sorry, I had it backwards before. I was looking at it backwards. Males had slightly lower chances, or the proportion of males who had high medical expenditures was slightly lesser than females. 9.33% of the males, 10.57% observed of the females. So let's just take this at face value to start. Without translating any of these results, is this result here consistent with what we saw in that table? The slope here for males is negative. What does that mean? That compared to females, males have lower what? Well, they have lower, right, exactly. I mean, log odds, right? Log odds, and hence they have lower odds, and hence they have lower proportion. So this is consistent, but on a different scale. So if we were to actually try and figure out this scale on our own and interpret these results, well, let's start as if we don't have any more information. Somebody came and deactivated status, so we've got to go to do this by hand for the moment, just so we can get a handle on what's going on. So I'm going to stop sharing that screen, and we're going to go back to a whiteboard. And what we have here is an equation that looks like this. Again, if I just write it on the right-hand side, negative 2.13 plus negative 2.135 plus negative 0.138 x1 or sex, where it's a 1 for males and a 0 for females. This looks like any regression equation, simple regression equation we saw in the linear case, but now if we look at what's on the left-hand side, it's the log odds of high medical expenditures. So if I go to a conference on pulmonary surgeons, right, and I present these results about medical expenditures, but I give them the resulting logistic regression equation to present my sort of findings about sex-based differences, is that necessarily going to be helpful for the audience to process? Probably not. I probably want to put this, do some legwork and put this into more commonly used measures of association, etc. So let's start with this negative 0.138. How can I interpret this? Well, most of you won't have to go through this level of detail, but it's probably helpful just to remind us once, is let's look at how many different groups, or how many different values of log odds, how many unique values are being estimated by this equation? Well, there's only two values of x, right? So we have males who are 1, and what? Their estimated log odds of having high medical expenditures is equal to negative 2.135 plus negative 0.138 times 1. Females, so this is for males. Females, the log odds of having high medical expenditures among the females, what's that equal to? That's just equal to the what? Intercept, right? So the only difference, if I was estimating the log odds, whether I'm estimating it for males or females, the only difference in the estimated log odds for these two sex groups, if I take the overall difference, what drops out? The intercept drops out. And just like we said before, this slope is just the difference in whatever we're estimating, pardon me, for a 1 unit difference in our predictor. The only possible 1 unit difference is 1 to 0, males to females. So this equals the log odds for males, I won't write the whole thing, minus the log odds for females. But as you so astutely told me before, when you see log minus log, the first thing you think of is what? Well, besides unbounded joy, you think of ratio, right? So another way to express this difference in log odds is the log of the ratio of the odds. So inside these brackets is an estimated odds ratio for the odds ratio of high medical expenditures for males to females. Of course, if I'm explaining this to an audience, I probably don't want to present this ratio in its log version and say the estimated log odds ratio comparing these groups is negative 0.138. It'd be much better to present the actual odds ratio. But how do I get it off that log scale? What do I have to do? I need to exponentiate. And if I do that, I'm going to get a value. Which is equal to 0.871 or 0.87. So, okay. So is that consistent with what we saw our individual proportions, right? It continually reminds us that males have lower odds, and if they have lower odds, as Emily said, they have lower probability, or a lower proportion of them have high medical expenditures. How might I present verbally this finding to an audience? I could say the odds ratio of having high medical expenditures for males relative to females was 0.87, but some people, upon hearing that, would not immediately process that that meant the odds, and hence the probability or proportion for males was less than that for females. How could I describe an odds ratio of 0.87 and make it clear that the males, the first group, had lower odds than the second? Any thoughts? Are you guys able to hear me? Can somebody thumbs up on that? I just want to. Okay, but generally you're able to hear me? Good. It's just the important parts that cut out, right? I'm sorry. So if I'm at a conference and I'm explaining this and I'm saying it would be totally appropriate to say the estimated odds ratio of having high medical expenditures for males to females is equal to 0.87. But some people might not process immediately or at all that indicates, because that ratio is less than 1, it indicates that males have a lower odds and hence lower probability, risk, or proportion of having high medical expenditures, at least in our sample. Is there any way I could express this 0.87 in another manner to indicate that it's a reduction? Perfect. Perfect. Exactly. So males, another way to say this is males have 13% lower. Is that necessarily lower risk? 13% lower risk, I mean? No, it is lower risk, but we don't necessarily know by how much unless we see the relative risk, right? Or risk ratio. One way I always remember this as a reduction is if you think of this, just to remind, colloquially that this is easier to interpret. I know everything's been shut down in many places because of COVID, but when stores were open, was there, at least in the US and perhaps Canada, the retail chain Macy's, was there ever a weekend where they weren't having a sale? Has anybody? They're forever having sales. So would they explain their sale, for example? So this weekend only, except until next weekend, right? All items, right? Would they say the sale price is 0.87 times regular price? Have you ever seen phrasing like that? Probably not. But they would say that the 13% off sale, right? So you can think that this language actually, you can even think of it as being borrowed from retail in some sense. Okay, so this is all good and well, but I know what you're thinking right now. A, it's getting towards the end of the day and everybody's busy, but why should we have to exponentiate if we bought stata, right? Shouldn't that be the minimum we can do above and beyond estimating this equation for us? And what I mean, when we say stata should exponentiate, it should exponentiate without us using it as just a straight up calculator, right? Don't you think it should be able to give us these results on that ratio scale? Well, it turns out, as you've seen, if I replace the command logit with the word logistic, it will present the estimates I got and their corresponding other line items on that scale. So this is that odds ratio 0.87. Let me ask you, let's go back to the logit scale. Is this result statistically significant? Well, this is the slope of a line, and regardless of what type of regression we're doing, if there's no association, a line has a flat slope, a slope of 0. So the null value on the slope scale, regardless of the type of regression, is always 0. Does this confidence interval include the null value? Yes, it does. Which means when we transfer this to the ratio scale, what would be the null value on the ratio scale? If two things I'm comparing are the same, then they're rate 1, right? So the antilog or exponent of exponentiated version of 0 is 1, and we notice that 1 is in the confidence interval on the ratio scale. So this is all good. This is more helpful perhaps than getting this output, but we'll talk about reasons why as we move through that this output may be helpful as well on the logit scale. One thing that Stata has finally done is it's flip-flopped over the versions between reporting the exponentiated intercept and not. And for a while, it would only report the exponentiated slopes and leave the intercepts out. But now, in the past few versions, it's also reported the exponentiated intercept. And that always gave me a little bit of pause because it puts everything under this column odds ratio. But is the intercept, an odds ratio implies that two groups are being compared by that value. Is the intercept comparing two groups? No, it is the value for one group alone, the group whose x is 0, right? And so I never was comfortable with it putting the exponentiated intercept in this column, but now they add at least a disclaimer to say, if we exponentiate the intercept, we don't get a ratio of odds, we get the odds for one group. And let me just to highlight that or formalize that, let's go back to the whiteboard for a minute. Let's see, where did that go? Oh, I guess I inadvertently erased it, but or somehow, oh, let me just stop sharing. So what I mean by that is, and we said when x equals 0, when we're looking at females, the log odds for that group is just the intercept. To get the log odds for males, we take the log odds for females, the intercept of negative 2.135, and add that slope for female. Okay, so you might say, John, this is a whole lot of nothing though, because this is great, but couldn't we just have much more easily done what we did in the beginning and gone ahead and just looked at that 2 by 2 table with the p-value? I mean, that gives us the proportions. We could estimate the relative risk for females to males by taking 9.33 over 10.57, and we'd be done. And we get this p-value, and notice that the p-value from the logistic regression, the overall p-value is for this is exactly what we got here, right? Does that make sense? So really, we're not doing anything differently here. We're just getting things on a different scale. And you might say, well, that's not nearly as useful a scale as the proportions. But if we wanted to, could we turn the results from a logistic regression? If we were not able to access that 2 by 2 table and did not able to empirically see what proportion of males and females with high medical expenditures, and all we were left with was this output, could we use it to estimate those proportions? And I think by the crescendo in my voice at the end, you should intuit that the answer is what? Yes, exactly, we can, but it's kind of painful, and it seems like something that's perhaps not that useful if we could really, in reality, just do a 2 by 2 table. But let me show you the connection. This will be useful moving forward. So, going back to our whiteboard here. So let's just think about taking this one step further. So if I have this whole thing here was to show that the slope could be is explicitly compares two groups who differ by 1, and it can be expressed on a ratio scale with exponentiation and odds ratio scale. But what about the odds for each of these two groups? Let's think about the logic here and the relationship between odds and proportions, okay? So I'm going to erase some of this here. And so it turns out, what is the relationship between the odds and a proportion, or the probability of something occurring, the way we define it? The relationship is what? Odds, how do we compute odds? It's equal to, right, p over 1 minus p, right? So the estimated odds for any one group based on their, so the odds of being high expenditure for any group based on sex in this case is equal to the proportion of those in the group who have high expenditures divided by the proportion who do not. Well, if we can express odds in terms of p, with a little bit of algebra, you can re-express p in terms of odds and show that if you had the odds for any group, you could turn that into an estimated probability by taking the odds for that group divided by 1 plus the odds for that group. This equation, when we plug in our value of x, we get an explicit computation for the log odds. I should say the natural log. So if we can compute the log odds for any group, we can convert that to the odds just by doing what? We can exponentiate it to get off. And then if we have the odds, we could estimate the proportion or probability of persons with the outcome. So for example, what I'm saying here is, if I look at females again, I've already written this, but the estimated log odds for females, I'm just rewriting this line here, is negative 2.135. And that means that the estimated odds, it would be what? E to that, right? I know it's late. You with me? Yep. And so the estimated proportion could be done by taking odds over 1 plus odds, or e to the, this is just for females, and then for males I could do the same thing but add negative 0.138 to this exponent. So let's see what happens. Let's go back to this data and see what happens when I do that. So if I do this, if I display E, and I'm just going to I'm going to copy the number directly from Stata here. Oh, sorry, I keep doing that. I get so excited to go to Stata, I forgot to, you know how it is. You see it now? If I divide by 1 plus that, I get 0.10569, the estimated proportion females. If I go back to that 2 by 2 table, what was the proportion given there for females? It's exactly the same. So if I have things on this logistic regression scale, they can be translated back to the proportion scale. You may say, in this case, John, that's just overkill, because you could have started with this, but what we're going to drive towards is when we have situations where our predictor is continuous, and when we get to multiple logistic regression, and we have multiple inputs, we can, based on the log odds estimated by the equation, we can estimate probabilities for different groups given multiple inputs at a time. How many people here have heard about data science? It's all you hear about, right, these days. It's a rebranding of statistics to some degree, but it also involves a bit more data wrangling and management as well. How many people here have heard of machine learning? Yep. And what is machine learning? Any thoughts? We see it pretty exactly. What is it? So prediction is what everybody wants to do, whether it's the medical world, the business world, etc. So machine learning is a way of predicting outcomes based on data inputs. And most of us are being machine learned. Our data is being used in machine learning all the time. Every time we go into Google, information is collected about us and fed into a big machine learning model to predict things like, are we more likely to choose Pepsi or Coke if we drink soda? Are we more likely to be a Mac user or a PC user, etc.? And that would actually is used to, target advertisements to us, etc. Right? So does that, but really the basis for a lot of machine learning, a lot of the joke among statisticians is a lot of it doesn't do much better than logistic regression for prediction. And so I'll expand on how we can predict at the individual level from logistic regression, but it is posited on the idea that given a bunch of predictors in a model, we can take the results from logistic regression and translate them into proportions or probabilities of the outcome given those inputs, and then use that probability to make a prediction about yes or no, will a person have that outcome. Okay, so I'm going to put the brakes on and leave it at this. I'll say one more thing about logistic regression, and then we'll jump back into this idea tomorrow and look at when we have a continuous predictor and see how that actually buys us something that we couldn't do easily with 2x2 tables, etc. And we can, like with linear regression, when our outcome exposure relationship where the predictor was continuous was well described by a line, we could get a lot of mileage out of that. The one last thing I'll say about this, though, is unlike linear regression, there's unfortunately no good measure, there's no good way to quantify how much variability in a binary outcome is explained by a predictor or predictors. So there's no R squared for logistic regression, but that doesn't stop something from appearing in the output. But what is the name of this measure? It's R squared, but what's the adjective used as part of it? Pseudo. What does pseudo mean? Fake. So, it kind of, whoever invented this must have an excellent agent, because it's pretty, there's a lot of chutzpah that goes into putting a quantity on your output that's labeled as fake. So there's no, if I said, hey, I have a pseudo car you might like to buy, would you be interested, So this quantity is not interpretable in any way, shape, or form as with the R squared from linear regression. So don't, luckily at least they put the word pseudo with it, right? So I will make fun of this for the rest of the course, but there's nothing we can do with this that's particularly useful, and it doesn't help us understand how well a model predicts the outcome, and we'll talk more about that when we start to look at more models and talk about the idea of prediction tomorrow on Friday. Okay, so we'll call it a day in regards to this. I'll hang out till about 10 after 5 in the lobby. Any questions, and certainly can hit me up on email or whatever, and we'll come back guns a-blazing tomorrow. I'm sorry, that was a bad analogy, just excited to get back into logistic regression and take it one step further, or 2 steps. All right? So I wish you a good Wednesday, and we'll be hanging around for a little while. Sure. Sorry. Yes. Oh, I'm sorry. I am muted. I'm sorry. Right. Okay. Great. Mm-hmm. Okay. Sure. Do you have your output there, Shoshana, that you can share, or? And if you don't, I can pull something up, so don't worry about it. I just was curious if you wanted to work off yours or mine. I'm happy to share. So. Okay, gotcha. So we have this. Can you see my screen? Awesome. So if I were to do on the logit scale, and we could type logistic as well, but if I did my outcome and age, right, is that how you would? That's how you would approach it, right? Just for the moment, just sticking age in. Age is continuous in years, and this is my result. So my resulting logistic regression equation is for any given age, the estimated log odds of having high medical expenditures is equal to negative 5.54 plus that age group's value times 0.0527, etc. Does that make sense? So if I'm looking at 51-year-olds, then my estimated log odds for that group is negative 5.54 plus 0.05 5.278, so 528 if you're okay with the rounding, times 51. Does that make sense? So that's just plugging 51 into the equation and seeing what we get, which is so far so good, Shoshana? Does that make sense? Great. So the log odds, so what we could say thus far is based on our logistic regression results, we estimate the log odds of 51-year-olds having high medical expenditures to be negative 2.8472. And of course, that is the value we get, but it's sort of hard to process. Well, what does that mean? So we can do a double transformation to take this to the probability of proportion scale to translate this into an estimated proportion of 51-year-olds who have high medical expenditures based on our results. So the first part of this transformation is to get this off the log odds scale to get, instead of the log odds, to get the odds for this group. So to do that, oh, go ahead. Perfect, yep. And keep going. Exactly. So this is the estimated odds for this group. If we want to express that as not an odds, but a probability proportion, we just take that odds of, like you said, 0.058, and I'm just copying this. I would not, unless I had the ability to copy and paste, I wouldn't do this, type it out to 8 decimals by hand. But if we do that, we get an estimated probability proportion of 0.055 or so. So about 5.5%. Does that make sense? Cool. Sure. Have a good evening. Oh, yeah, go ahead. Okay. About the, right. I'm sorry, that's a synonym for odds ratio. Yeah, sorry. That's the synonym, relative odds or odds ratio. I should have clarified that. Okay, great. See you later, Shoshana. Thanks. Hi, Amir. How you doing? I'm just emailing you, actually. So, yeah, no, I totally understand. I was just going to tell you in the email that I will post the videos. The only delay is I can't process the videos while I have Zoom open. It crashes my computer. So I will process them, which basically means I have to convert them to MP4s after class today and then upload them to YouTube. And depending on my internet speed, it'll be uploaded either tonight or tomorrow morning at the latest. But the first part of the class and this part will be recorded. Sure. So I'll try and remember to email you when they're posted. But if you don't hear from me by tomorrow morning, just check the course site. And today's session, the link should be there. Great. Thanks. Sir. Hey, Newham, hi. Okay. Part 3, okay. I'm just going to find it on my screen. So this is part 3, exercise part 3. I'll tell you what, Newham, part 3. Oh, exercise 2. I'm sorry. I'm looking at exercise 3. Let me open 2. I apologize. I was looking at the wrong thing. So you said exercise 2, part 3. Sorry. Here we go. Okay. All right, go ahead. Okay, share your screen, please. Yeah, that'd be great.